So I want to do a little review of finite dimensional vector spaces. I suppose you have seen real vector spaces over real numbers in a linear algebra class. So we are not going to sort of try to teach this. We just want to collect some basic facts about dimensions and so on that we need to study field extension. And the other thing that I want to point out is that much of this basic stuff that you probably have seen for vector spaces over real numbers do go through for vector spaces defined over any field without almost any change. The same proofs mostly go through. So you fix a field f. So if you want to be concrete, you can take f to be rational, so a set of rational numbers, a set of real numbers, set of complex numbers, or you could take these finite fields where p is a prime, so like f2 or f3 or something. A vector space V over F is an abelian group, V plus 0 together with a function dot from F cross V to V called scalar multiplication. And you write this as alpha comma V going to alpha times V. Sometimes you put a dot, sometimes you don't. Satisfying these four properties that 1 times V is V, alpha times beta times V is alpha beta multiplied first and then multiplied with V, alpha plus beta V is alpha V plus beta V, and alpha times V plus W is alpha V plus alpha W, and this is true for all alpha beta in the field and all VW in the vector space V. And in this context, you call the elements of V vectors and the elements of F scalars. So when you're talking about real number system, then the scalars mean real numbers. When you're talking about complex vector spaces, then scalars mean complex numbers and so on. So if you want to have some examples in mind, you have like, you could take Fn, the standard n-dimensional vector space, which is just n tuples of column vectors, let's say, or row vectors if you wish. So Rn, R3 means all such vectors, right? That's an element of R3. So instead of real numbers, you could take any, like you could take F3 cube. Now this is a finite dimensional vector space over F3. So this is going to be a three-dimensional vector space over F3. So its elements are all three tuples like this. But the entries come from F3, which means Z mod 3. So the entries can only be 0, 1, or 2. So this is a vector space of size 27, for example. Here we are also including such things. Okay. So you have Fn, you have n by n matrices over F, or more generally m by n matrices with respect to usual addition and scalar multiplication. You have various subspaces of this, which we'll talk about in a bit. You have something that we have seen, polynomial ring in one variable with coefficients in F, that's F vector space. You could take quotients of this, things that we have been studying lately. These are all examples. If you want to have infinite dimensional examples, this, for example, is an infinite dimensional example. You could also take things like in calculus, you see vector spaces like C01, which is like huge. This is like set of all continuous real valued functions. So these are all examples of vector spaces. So here you give me two functions, I add them, I get another function. You give me a function and a number, 3 times F is again a function, and those are the vector space operations. These kind we won't talk about much. We'll talk more about this kind. The ones that we really want to think about are these. Let V be a vector space, so really V is a 4 tuple, right? So you have to give a vector space, you have to tell me the set, you have to tell me the two operations called vector addition and scalar multiplication, and you have to tell me the 0 vector. So let this be a vector space over F. This is how we usually write it. A non-empty subset U of V is called a subspace. So that's the new word. If of V, if U with the operations taken from V, so this plus is the same as the plus of V, and this dot is same as the scalar multiplication of V, and this 0 is also borrowed from V. So U with the borrowed operations and the borrowed 0 from V becomes a vector space. So U itself becomes a vector space. So this is standard, and then you prove this usual lemma that how to detect a subspace. A subset of a vector space V is a subspace if and only if 0 is in the subspace, 0 is in the subset, and whenever two vectors are in this subset, then their sum is there. Whenever a vector is in this subset and you take any scalar whatsoever, then the scalar multiple is also in the subset. Yeah, so we say that U is closed under addition. When this happens, we say U is closed under scalar multiplication, and U contains 0. That's how you say something is a subspace. Like here is the vector space R2. This is a subset that is closed under addition, because if you take any two vectors here, you add, it's still in the shaded part, but it's not closed under scalar multiplication, because if you take a vector in there, its negative multiples are not shaded, not in the shaded part. Yeah, you could try to make it closed under scalar multiplication by adding that, but now it's not closed under addition, because if you take a vector here and a vector here, then the sum of those two, which is here, is not in the shaded part anymore. It turns out the subspaces of R2 are what? The subspaces of R2 are simply R2 itself, the lines through the origin, and then the origin itself. Yeah, so maybe in this list I forgot to include the 0 vector space. That does satisfy the axioms. The single element set, where all the operations are trivial. Okay, so that's subspace. So the subspaces of the three-dimensional real vector space are, there are 4 kinds. So now here is R3. So there's the origin, then there are the lines through the origin, then there are the planes through the origin, and then there is R3 itself, etc. Okay. Next we need to talk about all these notions of linear combination, span, linear independence, and so on. So let's have this setup. V is a vector space over F, and you have a bunch of vectors v1, v2, vm in V, and I'll write S for the set of these things. But I do not want to think of the set. I might be repeating some vectors in this list, so I just want to think of the list. Let v1, v2, vm in V. A linear combination of v1, v2, vm is just a vector, so that's the new word. A linear combination of v1, v2, vm is a vector v of the form alpha 1 v1 plus alpha 2 v2 plus alpha m vm, where the alphas are scalars. Yeah? So I don't know, if you give me a, here is a vector, here are 3 vectors in R3. If I take this one minus that one plus 3 times that one, let's say, what do I get? Maybe I'll take that one. I'll get 3, 2, 3. So I'll say that this vector 3, 2, 3 is a linear combination of this v1, this v2, and this vt. because I've written it as a scalar times the first one, plus a scalar times the second one, plus a scalar times the third one. We say that this vector is a non-trivial linear combination of v1, v2, vm if one of these coefficients is non-zero at least. So of course you can take 0 times v1 plus 0 times v2 plus 0 times vm. That is a linear combination, and that would happen to be the zero vector. But that we'll call the trivial linear combination. Anything else we'll call a non-trivial linear combination. Some coefficients could be zero, but at least one of them have to be non-zero. So this here is a very much non-trivial linear combination, this one. Okay. So then you verify, this is a little exercise that you do, you verify that the set of all linear combinations of v1, v2, vm is the smallest subspace of V that contains these guys. And this thing is called the span of v1, v2, vm, and denoted by span of S. Yeah, so if you give me, in this picture, this example that I gave is in something in R3. We have three vectors, 1, 1, 1, and then 1, negative 1, 1. I'm not drawing them honestly, I'm just drawing some cartoon. And then there's a third one, but you realize that the third one is really the first two added divided by 2, so it's really the midpoint. Here's the third one. So if you take all the linear combinations of these guys, you're just going to get this plane, because the third one just happens to fall in the plane that contains the first two. So here is v1, here's v2, here's v3 right in the middle. So this is, for example, v1 plus v2. And then v3 is half of v1 plus v2. And then here, for example, is v1 over 2 plus v2. So these are all linear combinations. Yeah, this one, for example, is v1 plus v2 minus v3. And so if you go half the other way, yeah, or rather v3 minus v1 minus v2, etc. So if you take all linear combinations, you just get all vectors in this plane. So this plane is the span, in this example, the span of S. And if you have a subset of VU and a subset S such that U is span of S, then we say that U is span of S, or S is a spanning set of U, or that S spans U. These mean the same thing. Okay? So S is a spanning set for U if and only if every vector in U can be written as a linear combination of elements of S. Yeah, so this plane has a spanning set v1, v2, v3 here, means that every vector in this plane can be written as some multiple of v1 plus some multiple of v2 plus some multiple of v3. Well, I don't really need v3, but throwing in v3 does not hurt. Okay? And then we'll stop with this definition. Once we have this notion of a spanning set, we say that V is a finite dimensional vector space if V has a finite spanning set. So you can write every vector in V as linear combination of a finite set of vectors. So there is a one finite set that I can give you, so that every vector in V can be written as linear combination of these finitely many vectors. Okay? So that's the notion of a finite dimensional vector space. So next we'll talk about linear independence and then get to basis.